Hello, everyone. What I want to do now is actually finish up talking about Hilbert spaces. I know I said the last video we were done, but I do want to do a application of the Riesz representation theorem to kind of giving you a glimpse into showing how Hilbert space methods are used to prove existence results for second order partial differential equations. We're only going to really just scratch the surface, and I'll just really prove the existence of weak solutions to a very special second order differential equation, just because I don't want to spend too much time on it. I can really spend half a semester probably on Sobolev spaces and existence of weak solutions to partial differential equations. I just want to do something in one lecture. Okay, so first I need to talk about the completions of Hilbert spaces. Okay, so let's say X is an inner product space. So to abbreviate that, INP, inner, sorry, I don't know why I did that, IPS, inner product space. All right, just remind you of the completion, which I called X star, probably not good notation because that's usually reserved for the dual space, but anyway, that's all right. Remember, it's the set of all classes of Cauchy sequences of X. And here, remember that two Cauchy sequences, xn and xn prime, are equivalent if xn minus xn prime converges to 0 in norm. So, right, so everything we've done tells us, we have, if we have an inner product space, we have a normed space. So we have a Banach space. I'm not going to rehash everything I've done. I just want to give this a inner product, which makes this a Hilbert space. If X is an inner product space, it's not necessarily complete. Okay. So in particular, you can kind of give this the obvious inner product. So let's define the inner product as follows. This limit xn, yn, and to be precise, this is, I'm defining this to be the following. Where x hat is going to be this class here, and y hat is going to be this class here. So again, the first question you should ask is, well, does this make sense? Is this well defined? Is this independent of the representation picked for x hat and y hat? And the answer is yes. I'll very quickly outline this. It's very easy. So let's say xn is equivalent to xn prime, and same thing for yn. Let's say we also have yn is equivalent to yn prime, excuse me. Then we have xn yn minus xn prime yn prime is going to be equal to, I'm not going to fit this here, don't even want to attempt it, so let's do it over here. It's going to be equal to just adding and subtracting xn prime inner product yn. We get xn minus xn prime yn plus x n prime yn minus yn prime. And again, this is x. Everything is an x here. I won't write it here, but I guess I'll write it real quick. This is an x, an x. And you can use Cauchy-Schwarz inequality to get that this goes to 0, because xn minus xn converges, sorry, xn is equivalent to xn prime, so by definition the norm is 0 of xn minus xn prime as n goes to infinity. Same thing, yn is equivalent to yn prime. So a norm, yn minus yn prime converges to 0 as n goes to infinity. Well, yn and xn prime are Cauchy and hence bounded. So by the Cauchy-Schwarz inequality and the triangle, just triangle inequality for absolute value, this is 0. Okay, so this is well defined. So that means this x star here is a Hilbert space. Which is very important because, as we've seen, and as you've probably learned in many different contexts, Hilbert spaces are wonderful, they're amazing. If you can recast things using Hilbert spaces and use Hilbert space techniques, that's great because basically everything you could ever want goes well in a Hilbert space. Okay, so let's talk about Sobolev spaces in the context of Hilbert spaces. And again, I'm only going to absolutely scratch the surface. If you want to know more about about Sobolev spaces and partial differential equations, my favorite book is Lawrence Evans' PDE, partial differential equations. It's a big book. It's like 600 pages, but it really does things in a lot of detail. It's really just a good book. I personally love it. I believe it's an AMS graduate book, American Mathematical Society. Maybe actually it's online, so maybe I'll put a copy of the PDF. Anyway, maybe not. We'll see. On Blackboard, probably shouldn't. Anyway. Right, so nothing, we in homework talked about the Sobolev space before, so I'm just going to remind you of the situation here. So here I'm going to deal with real Hilbert spaces. Usually when dealing differential equations, you deal with a real Hilbert space. You don't really have to, but particularly for PDEs, PDEs with complex solutions are kind of nasty and very difficult to study. So you often avoid doing that. Right, so remember C12 is a set of all F from 0 to 1 to R, where F and F prime are continuous. F has a first derivative on 0 to 1. And the C12 norm is finite. Okay, so this is, I'll remind you what the C12 norm is by telling you what the inner product is. So this has an obvious inner product. 0 to 1, f of x, g of x. I should mention Riesz representation theorem. Everything we've done absolutely works for real Hilbert spaces. The only difference is it's actually a little easier. You don't need to worry about putting a stupid little bar in certain places. I shouldn't say that because I do a lot of complex analysis, obviously. So it's maybe not stupid. But anyway, right. I should say in some contexts, particularly when doing several complex variables, you do want to absolutely look at Hilbert spaces, or you do want to look at complex solutions to partial differential equations. But anyway, right. So the C12 norm is just f inner product f raised to the 1/2. So, and this is for f and g in C12. This is certainly not, as we've seen, not complete. C12. So we do not have the Hilbert space tools available to us. So we do the next best thing. We just complete it. And I do not understand for the life of me why anyone ever used W for the Sobolev space, but they do, so I feel obliged to also use W. As I said in the homework, you usually do this over a open set of Rn for some integer n, but we're just going to keep things simple. Like I said, to really properly do Sobolev spaces and weak solutions differential, the PDEs would take a month really, and don't really want to do that. Unless people do want me to do that, I guess we can do that, but anyway. Okay, right, so let's say we have gamma in, I just used gamma in the homework, so not very, I have to admit, I'm not very consistent with notation, but hopefully I'm not, at least not using confusing notation. Okay, so what is gamma? Well, remember, gamma is really definition a class of Cauchy. It's gamma is a Cauchy sequence essentially. It's the class generated by this Cauchy sequence. So this is Cauchy in C1, 2, and I'm not going to write 0 to 1 now on. It's kind of a pain. So what does this mean? Well, from homework, we have two properties. We have that Fn converges to some f, and Fn prime, because this is Cauchy in C1, 2, this converges to some big F in L2, just because L2 is complete, nothing more than that. So this is an L2, and this is an L2. Also, for anything very nice, particularly for phi in CC1 of 0, 1, what on earth does that mean? That means that phi is continuous and has a continuous derivative on 0 to 1. and phi is 0 away from a closed interval contained in 0 to 1. So the C here means it has compact support. Away from a closed interval of 0 to 1, phi is 0. Okay. So for any phi in C, C1, 0 to 1, we have the following is true. It was basically just really nothing much other than just a little easy approximation argument involving limits and Calc 1 integration by parts. So this is going to be given by 0 to 1, f of x, phi prime of x, dx. And remember, kind of the punchline here, the part of the homework was showing that if big F actually is the actual derivative of little f, and big F is continuous on 0 to 1, then this is true. So in some sense, big F is like a derivative of little f. In some sense. I mean, little f, there's no reason why little f needs to be differentiable at all. I mean, you do have some results from 510a or maybe stuff. There's some like real analysis stuff in Follin's book on differentiability, but those go out the window when you talk about partial derivatives and do this stuff with partial derivatives. That's really the point. Again, we're just doing things on 0 to 1 to keep it nice and simple. But anyway, so yeah, the point is that in some sense, big F, big F is sort of like f prime in a weak sense. And in some sense, big F is like the derivative of little f. We call this a weak derivative because it's, in some sense, it behaves like the derivative of little f. So let me write this as an asterisk. So this is actually unique. What do I mean by that? Sorry about that. Well, if star is true for f and g, then for any phi in CC1 of 0 to 1, what do we have? We have f of x, phi of x. Well, we're assuming it's going to be this here. F of x. And we're assuming we have two functions, big F and g, that satisfy this. Whoops, sorry about that. And the point here is that this is true for any phi in CC1 of 0 to 1. Well, this is dense in L2. So maybe to make clear, we're saying this is in L2. Let's say L2. More generally, we could just assume it's in L1, but whatever. Yeah, so that means F equals G in L2, particularly almost everywhere, because this is true for all phi. Okay, right. So from now on, and I have to admit, this is a cumbersome way of defining the Sobolev space. You often define the Sobolev space directly in terms of weak derivatives. That just takes more time. It's more natural, um, but anyway, right. So let's say we have a gamma in the Sobolev space W1, 2. So from now on, I'm going to associate this with f and little f and big F. Okay, so for each gamma, there is this Cauchy sequence. And from this Cauchy sequence, Fn and Fn prime are Cauchy, so they converge to something little f and big F and L2. And you can check, I'm not going to, maybe, I don't even know if I'll give this for homework, maybe, but you can check this is independent of the class chosen. If Fn, the Cauchy sequence Fn, is equivalent to Fn tilde, then you get the same little f and big F. There's really not much there because equivalence is saying as n goes to infinity, Fn minus F tilde n in norm is 0. And you can show very easily then that Fn tilde converges to little f, Fn tilde prime converges to big F. So this is definitely well defined. And you can check very easily, again, kind of like the homework, just easy taking limits, that if I have, let's say, a beta in, I don't know why I call it beta, but just lack of anything better to call it. And let's say beta, by the same procedure, is associated to this pair, little g and big G. And again, of course, this is a pair kind of f and f prime in some sense. This is like the weak derivative of little f, this big F. So here's G and its weak derivative, big G. And I'm not, like I said, not that I'm going to use it, but this kind of weak derivative business is unique, which is nice to know. I don't think I'm going to use it actually, but yeah, right. So you can check using the definition that I wrote down at the very beginning, the definition of the inner product for a completion of an inner product space, that this will actually turn out to be exactly 0 to 1 f of x. And again, everything is real valued here, so no bar. Plus, well, in some sense, f prime of x, g prime of x. Well, really, it's big F and big G. Okay? And again, I'm saying this is like a little, you can prove an easy homework. I don't know if I'll collect it or not, but maybe I will. Right, and this is W1, 2. Okay, right, so let me talk very briefly about weak solutions. To ODEs. And again, usually you want weak solutions to PDEs, and I'm particularly going to talk about second order ordinary differential equations. Right, so let's say f is a function on 0 to 1, And let's say it's twice differentiable. So in particular, f and f prime are continuous. Okay. So let's play a similar integration by parts game that we did in the homework and we just did. So for phi in CC1 of 0 to 1, if we have that minus f prime, f second prime of x plus f of x equals h of x for some function h of x, well, if certainly f is continuous on 0 to 1 because f prime is continuous. So at least h of x is continuous on 0 to 1. Okay. So if this is true in the ordinary classical sense, and I'm picking this ODE here, so here I should say this is like a given. So we're kind of assuming f is satisfying this ODE here. H is just some given function. And I'm picking this ODE because this is really the ODE that, well, I'll talk more about that later. So let's see what happens here when I multiply everything by phi and integrate. Okay. So I'm going to get the following as true. 0 to 1, f prime prime of x, phi of x, dx. Let's do integration by parts. I can dump a derivative onto phi prime. Phi of 0 is phi of 1 is 0 because phi vanishes outside of a closed subinterval of 0 to 1. The open interval 0 to 1. So by integration by parts, calc 1 integration by parts, this is 0 to 1 f prime of x, phi prime of x, dx. Okay. But what is this really here? Well, this is going to be equal to, well, let me do it on another page here. So this means that, let's see. Right, so let me write down what this means. 0 to 1, f of x, phi of x. And this should look curiously similar to an inner product I talked about just a moment ago. Okay, so this is going to be equal to, well, again, this is going to be minus, let me write it like this, 0 to 1. F of x. Yeah, sorry, minus f second prime of x. A little brain fart there. Sorry about that. Well, all times phi of x. Because, right, because this this one here, integral f prime of x, phi prime of x, is minus integral 0 to 1 f second prime of x, phi of x. So we have a common phi of x here. All right, but we know what f second prime minus f second prime plus f is. It's just h. So this is going to be 0 to 1 h of x, phi of x. All right, so in some sense, and you can actually show that, I won't do it, but if what I have in red is true for all CC1 0 to 1 functions, then and f prime and f second prime are continuous on 0 to 1, then this has to be true. Okay. Right. So we basically, in some sense, recast. If it's an if and only if statement, which I'm claiming it is, but I'm not going to prove it, then we've kind of recast my differential equation in a way that looks awfully like the Hilbert space stuff for the Sobolev spaces that we've been talking about just a moment ago. Okay. Let me be a lot more clear. So let me make a definition. So by definition, I want to extend what it means for this differential equation to be true, not necessarily for actually differentiable functions, but for weakly differentiable functions. So a pair gamma, which is associated to little f, big F, so remember, this is something in my Sobolev space. Is a weak solution to, say, star. Did I do star already? All right, let's do star star. And sorry, what is star star? This is star star right here. If for any CC1 function on 0 to 1, basically we have this is true, except, well, we don't know what f prime might not exist, but this big F is kind of like the next best thing. So exactly, sorry about that. Yeah, so we have to have that 0 to 1. Let me do it exactly like here. F of x, phi of x, plus big F, or sorry, 0 to 1, f of x, phi prime of x. No ambiguity for phi prime, of course. Phi is absolutely normally, traditionally twice differentiable. Right. 0 to 1, big F, sorry, h of x, phi of x. So why on earth do we want to do this? Why on earth would I ever want to do this? And that's a very good question. Well, with this definition, I can prove, and I will do that in a moment, that weak solutions to this differential equation always exist. And I can assume actually that H is just L2. So that's often when you have like a differential equation or a partial differential equation, proving the existence of weak solutions is basically pretty easy. And then what you often do is put a lot of work into showing that actually your weak solution is a regular traditional solution from basically from this property here. For any CC1 of 0 to 1, you prove properties about your pair F and big F. Right, and you usually do this in the context of partial differential equations. Okay. Right. Okay, yeah, so let me finish this off by the following proposition. Basically proving existence of weak solutions. So if H is an L2 of 0 to 1, then there exists unique gamma in my Sobolev space W1, 2. Sorry, I should say there's a unique weak solution little f and big F gamma basically is little f and big F. 2 star star. Okay. Right. Okay. And really the beauty here is that there's not a whole lot to the proof. No point in doing that really, but proof is just Riesz representation theorem, literally. Okay, well, if I claim the proof is Riesz representation theorem, I need a bounded linear functional. Well, there's really not, well, let's define bounded linear functional as follows. Right, so, right, so let's say beta is again, maybe beta is just something in my Sobolev space W1, 2, and that's associated with little g and big G. Yeah, so this is in W1, 2. Okay, so define the following bounded linear functional. I need to prove it's bounded, but so let's say it's going to be 0 to 1, this integral of h of x little g of x. Well, this is fairly obviously linear, x. And there's really not much to prove. It's bounded. So by Cauchy-Schwarz inequality, this is obviously less than or equal to L2 norm of H, L2 norm of G, which is obviously less than or equal to L2 norm of H times the L2 norm of little g plus L2 norm of big G, which is equal to L2 norm of G times the Sobolev space norm of, sorry, not gamma, of, I do beta. I did use beta. That's good. Remember in the homework, the L2 norm of beta was little g L2 plus big G L2. Right, so this is a bounded linear functional. So by the Riesz representation theorem, there exists unique, exclamation mark is for unique. Let's say unique gamma in W1, 2. Okay. So this is why we need completions, because we want to use Riesz representation theorem, and that absolutely depended on completeness. Gamma is F, big F, where L, H, beta equals beta gamma for any beta in W1, 2. Okay, that's what the Riesz representation theorem says. Given any bounded linear functional, that bounded linear functional is basically given by the inner product with some element in your Hilbert space. Okay, and really, usually in PDEs, this is really overkill. You don't really need this for all beta in your Sobolev space, because particularly all you want to do is basically apply it to your, this function right here, which is often called a test function. When you're trying to prove properties about weak solutions, you often throw in all kinds of ingenious test functions, and they can get really, really ingenious. But to do that first, you got to prove that there is such a f, little f and big F, where this is true for all stuff in CC1, 0 to 1, which is what we're doing. Okay, right, so, our task is to prove that gamma is a weak solution. Let's show that. So if phi is in CC 0 to 1, and let's do something kind of silly. Beta is just a class generated by this constant sequence. Certainly this is in C1, 2. So beta obviously is associated to phi and phi prime being the actual ordinary, regular, traditional, whatever derivative of phi. Okay, right, so let's just write down what is, excuse me, sorry about that. Right, so let's, for this beta here, let's write down what this even means. Beta gamma. Sorry about that, I meant gamma here. And this is W1, 2. Okay, right, so this here, remember what the definition is. It's just 0 to 1 h of x, g of x. So here, well, this is just phi, so it's 0 to 1 h of x, phi of x dx. And this is good. This is the one second. Yeah, sorry. This is the right-hand side of what I need to prove, or what I need. And I need to show that this is going to be given by this here. So we have 0 to 1 h of x, phi of x. this is going to be, let's write out what the, what I said was the inner product. It's going to be 0 to 1 f of x. Well, here this is 5x. And then big F phi prime of x. So it's 0 to 1 f of x phi of x plus 0 to 1. So I guess it really should be phi of x, f of x, but it doesn't matter. Everything's real, so yeah, so maybe make it a little clearer. This is the same thing as gamma beta. Right, so it's going to be big F of x, phi prime of x. And lo and behold, that's exactly what we want. 0 to 1 f of x, phi of x. 0 to 1 big F phi prime. That's exactly what I have here. F of x phi, big F phi prime, equals integral 0 to 1 h of x phi of x dx, which is exactly what I have on the right-hand side here. And certainly, as I mentioned, every phi, you can cook up something in your Sobolev space as follows. So this is true for any phi in CC1 of 0 to 1. So using functional analysis tools, Rees representation theorem, we have managed to prove existence. Well, there's a unique element. There's a unique element, gamma, associated to little f and big F, where this is true. Okay, so we've managed to prove particularly uniqueness and existence of weak solutions to this differential equation right here. Okay, so well, this kind of asks the question: what if you want to look at something other than this? So in that sense, Rees representation theorem really is kind of not so good. It really doesn't work for anything else. So what do you do for other ODEs, other second order ODEs, and well, what you really care about is second order PDEs? Well, you have what's called the Lax-Milgram theorem, which is a very beautiful and powerful generalization of the Rees representation theorem. And basically, this is a corollary of this theorem here is really a corollary of the Rees representation theorem. But this Lax-Milgram theorem, which I won't get into, this is really the tool to prove the existence and uniqueness of weak solutions to other ODEs, and if you want to play this game in higher dimensions, to other PDEs, second order ODEs and second order PDEs. Okay, right, I'm gonna stop here. You know, I mean, again, if people are really interested in this, I'd be happy to talk more about this and get into particularly elliptic PDEs, second order elliptic PDEs. That's what I'm interested in. I'm really interested in systems of elliptic PDEs, or rather elliptic systems of PDEs. But anyway, all right, hopefully this was interesting. And again, Evans PDE is probably the best source if you're interested in doing this further. There's an excellent chapter on Sobolev spaces that really does it carefully and properly. But enough rambling. All right, so long. Take care. Bye bye.